One agent gave me a confident answer that was completely made up. 3 agents code the same Y in 2 rounds, and the fix is just a loop. You know that feeling when an agent answers so confidently you just trust it. That's the trap. A single model has no idea when it's wrong. It just asserts, ships the answer and moves on. So today we stop treating hallucination like a model problem and start treating it like a coordination one. So the fix is basically peer review for agents. You spin up 2 or more agents that answer the same question independently, then a cross-examination node makes them attack each other's reasoning and actually cite evidence. They loop until they agree on something verifiable. And the whole thing runs as a LangGraph state machine. But the magic isn't the agents, it's where the loop lives. Alright, here is the setup. Everything lives in one shared graph state, including a scratch pad holding the debate transcript. Each agent writes its verdict as a Pydantic model, so the consensus check is structured and not vibes. Then a conditional-edge reads the state and decides loop back or escalate to a judge. Notice that the debate is just an edge pointing backward. It will make more sense once you see it in the code. Alright, you have seen the whole flow. 2 agents, a debate loop, a judge for the tie break. Now let's get the project set up. We need 3 things. One graph for the state machine, one chain anthropic for the agent calls, and Pydantic for the structured verdicts. And after that we have to set our anthropic API key. Here you should replace it with your own key. Next we create the schemas.py. Now this is where we make consensus checkable instead of a vibe. The verdict class is that structured output we talked about earlier. Each agent has to fill in an answer, the evidence behind it, and one boolean whether they agree with their peer. That boolean is the entire convergence signal. The state is just a shared dictionary that flows through the graph, and the transcript is our scratch pad. Notice that it uses operator.at, so every node appends to it instead of stomping on it. That's how we keep the full debate history. And now we create the nodes.py. This little helper is what every agent runs. We point it at the model, then wrap it with the structured output, so the reply comes back as a verdict object and not raw text. No parsing, no regex, just typed fields. The peer argument is the key detail. On the first round it's none, so the agent answers code totally independent. On later rounds, we hand it the peer's verdict and the prompt tells it to either agree or attack their reasoning with evidence. That one helper powers both the proposing and the cross-examination. Same function, different inputs. Now we have to define this helper function, which will come in handy in a second. And now the actual debate. The proposed node runs both agents with no peer, so we get 2 competing answers, fully independent. That's round 1. The cross-examine node is where it gets interesting. We run each agent again, but this time we feed it the other agent's verdict. So agent A sees agent B's answer and agent B sees agent A answer, and each one gets a shot at tearing the other apart or conceding. Notice what we walk each round. Not just the answer but the evidence and that agree flag. That flag is the thing we will watch flip later. Every round appends to the transcript, so we never lose the history. This is the brain of the loop. The route function looks at both verdicts and makes one call. If the answers match or both agents flip their agreed flag to true, we're done, straight to finalize. If we hit max rounds and they're still fighting, we stop and send it to the judge. Otherwise, back into the cross-examine for another pass. The judge is just a separate model call that reads the whole transcript and picks the best supported answer. It's the tiebreaker, so the graph never loops forever. And finalize just pulls out the agreed answer. Those 3 small functions are your entire control flow. Inside the graph.py, we assemble the graph. We spin up a state graph, typed on our debate state, then register all 4 nodes. Propose, cross-examine, judge and finalize. Right now they're just floating. They're not connected to anything yet. The wiring is the next part, and that's where the debate loop actually comes to life. And here is the part that makes this debate instead of a straight line. We started propose and then flow to the cross-examine. After that the conditional-edge takes over. It runs our route function and sends the graph one of 3 ways. Look at the mapping. Cross-examine can point right back to cross-examine. That backward edge is the entire debate loop. The agents keep arguing until route says stop. Judge and finalize both go to end. We compile and that's a working peer review state machine. Now let's prove it. We ask one model a question with a trap in it, the kind of thing it will answer confidently and get wrong. That's the single agent. Nobody checking it. Then we run the exact same question through the graph and print the consensus. But here is the part that actually sells it. We dump the full transcript underneath. When we run it, you should pay attention to the agree flag and the reasoning. Let's now see it in practice. Let's run the graph.py. Alright, let's inspect the output. We can see that the single agent actually answered correctly, but that's not the point. The more interesting thing is to see what happened in the debate. You can see that on round 1, both agents agree flags are false. On the next iteration, when they know the answer of their peer, you can see that agent A agrees with agent B, but agent B doesn't agree with agent A. And that's why they go to the third round, where agent A again agrees with agent B, and agent B this time agrees with agent A, and so they reach the consensus. If you're more interested, you can pause here and inspect the outputs. But the takeaway is that the agents were able to debate and reach a consensus with either agreed rounds. So now you have got a graph that doesn't just trust its own first answer. You've got multiple agents giving independent takes, a cross-examination loop that forces them to defend their reasoning, and a conditional edge that keeps them debating until they actually converge. That hallucination one agent swore was true, caught and corrected before it ever reached the user. Next step, swap in your own domain agents and tune that similarity threshold for how strict you want consensus to be. Then try a judge model for the tie breaks. And if you want more agent patterns like this, hit subscribe. I'll catch you in the next one.